Recording in progress. Welcome to our class today, June 7th, 2022. I will start talking about the group final project in this course. Tomorrow, a full group sheet with names will be announced via OWL. I'll put some due dates for picking the project name and type, like a guide about the progress report, how to be written and submitted. I will open also an assessment and assignment and assessment task in about the progress report, due date, how to finalize the project type or the project name, topic with me and with the course TA. All of these things will be announced tomorrow. Also, I need to talk with you guys about the final exam, when it will be. I believe based on our calendar that last day of our course is August 9. I believe August 9 or 10. Let me open the engineering website. Okay, yeah, it's August 9. Let me share my screen so you are aware where I am. So here our course would be in August 9. Our project presentation, this room is reserved for us because as I told you that project presentation would be in person and the final exam would be in person. So August 9 is Tuesday. So we will have our final exam on the same, but I'm not sure about the room size. Action, are you here?
Yes, Muhammad Noor, I'm here.
Okay. Could you please check this room and see if it is suitable to accommodate like 35 students for final exam?
Yeah, for sure.
So please check it and let me know. If that is the case, then we'll have our final exam on the same as a class Tuesday, August 9 from 8:30 to 11:30 as a final exam.
Yeah, sure.
Yeah, and if it is not, please let me know so we can book another room.
Yeah, for sure.
Okay, thank you, Afshin.
Of course.
So once you check, please just email me and let me know.
Okay, sure.
Okay, thank you. So let's from now decide that our final exam would be in like our last class. Our last class will be our final exam, in-person exam. And for the project guidance, instructions, all things related will be announced by tomorrow evening maximum. Any questions about this? And also the deadline, which will not exceed next week class to pick your project topic. One of the group member can contact us once I announce the group numbers. Then you can email me and Afshan, the course TA. So this is the topic we will choose. This is what we will do. Then we can send you the approval to go ahead, or we can have like a quick Zoom meeting on Monday during my office hour or any suitable time for you guys to discuss the project type. I need those to be done by next Tuesday. Those should be finalized in order to give you enough time to work in the progress report and your project. Is that okay? Questions? And also I want to share something because I feel some students, I don't know what's their reason, circumstances happen suddenly, but I feel the attendance is not up to the accepted level. We have 3 students auditing the course. I believe they are with us. So it is 24 out of 34 normally, the average of attendance of the already registered student in the course, which means 10 students, they are absent, which is not acceptable at all. And there is exam, we have 40% and 60% for the project. If I'm correct, no, not this. We change it a bit. Yeah. So let me share my screen. And I will send an announcement on this, that class participation is not only, we have 10% as a class participation. This is not only if you answer the any class question and submit it in the Google Drive. Also, your actual attendance is part of this mark. So for those who are absent, guys, I'm talking because I believe they will watch the recording. I know that you are attending, you are regularly attending, but for those who are absent, that 10% will be affected negatively and will affect their final course mark. Because in Zoom, I use the automatic attendance, and it's also showing me if the student just open his screen and leave, then at the end of the class, normally 3 to 4 students, I sign them out from the meeting, which means they are not there. They just open just to record an attendance. So I don't know, it's your call. It's a graduate course. You are not an undergraduate, so you are mature enough students, and you know what is good at your side and what is bad. So just as a reminder, I believe like there are in some classes and sometimes that you have emergency thing that you will not allow you to attend. I understand all these circumstances, but some of the students, they didn't attend any class since the beginning. So it's their call. Just I make like a quick reminder for those. We will start our class in optimization today. So just let me know how is the sound and how is everything.
Fancy word for finding the best way. We can.
Is it okay?
It's okay. It's clear. Thanks.
Okay.
Optimization is a fancy word for finding the best way. We can see how it works if we take a look at drinking tea. There's a best temperature for tea. If your tea is too hot, it'll scald your tongue, and you won't be able to taste anything for days. If it's lukewarm, it's entirely unsatisfying. And there's this sweet spot in the middle where it's comfortably hot, warming you from the inside out all the way down your throat and radiating through your belly. This is the ideal temperature for tea. This happy medium is what we try to find in optimization. That's what Goldilocks was looking for when she tried Papa Bear's bed and found it too hard, tried Mama Bear's bed and found it too soft, and then tried Baby Bear's bed and found it to be just right. Finding how to get things just right turns out to be a very common problem. Mathematicians and computer scientists love it because it's very specific, it's well formulated. You know when you've got it right, and you can compare your solution against others to see who got it right faster. When a computer scientist tries to find the right temperature for tea, the first thing they do is flip the problem upside down. Instead of trying to maximize tea drinking enjoyment, they try to minimize suffering while drinking tea. The result's the same, and the math works out in the same way. It's not that all computer scientists are pessimists, but just that most optimization problems are naturally described in terms of costs, money, time, and resources, rather than benefits. In math, it's convenient to make all your problems look the same before you work out a solution so you can solve it just the one time. In machine learning, this is often called an error function because error is the undesirable thing, the suffering that's being minimized. It can also be called a cost function, or a loss function, or an energy function, but they all mean pretty much the same thing. There are a handful of ways to go about finding the best temperature for serving tea. The most obvious is just to look at the curve and pick the lowest point. Unfortunately, we don't actually know what the curve is when we start out. This is implicit in the optimization problem. But we can make use of our original idea and just measure the curve. We can prepare a cup of tea at a given temperature, serve it, and ask our unwitting test subject how they enjoyed it. Then we can repeat this process for every temperature across the whole range that we care about. By the time we're done with this, we do know what the whole curve looks like, and then we can just pick the temperature for which our tea drinker reported the most enjoyment, or the least suffering. This way of finding the best tea temperature is called exhaustive search. It's straightforward and effective, but it might take a while. If our time is limited, it's worth it to check out a few other methods. If you imagine that our tea suffering curve is actually a physical bowl, then we could easily find the bottom by dropping a marble in and letting it roll until it stops. This is the intuition behind gradient descent, literally going downhill. To use gradient descent, we start at an arbitrary temperature. Before beginning, we don't know anything about our curve, so we make a random guess, and we brew a cup of tea at that temperature and see how well our tea drinker likes it. From there, the next trick is to figure out which direction is downhill and which is up. To figure this out, we choose a direction, again arbitrarily, and we choose a new temperature a very small distance away. Let's say we choose to the left, cooler temperatures. Then we brew up another cup of tea at this slightly lower temperature and see whether or not it's better than the first. We discover that it's actually inferior. Our tea drinker likes it less. Now we know that downhill is to the right, that we need to make our next cup warmer to make it better. We take a larger step in the direction of warmer tea, brew up a new cup, and start the process over again. And then we repeat this. We do it over and over until we get to the very best temperature for tea. The steeper the slope, the larger the step we can take. And we'll know that we're all done when we take a small step away and get the exact same level of enjoyment for our tea drinker. This can only happen at the bottom of the bowl where it's flat and there is no downhill. There are lots of gradient descent methods. Most of them are clever ways to measure the slope as efficiently as possible and to get to the bottom of the bowl in as few steps as possible. They're all tricks to brew as few cups of tea as we can get away with. They use different tricks to avoid completely calculating the slope or to choose a step size that is as large as can be gotten away with. But the underlying intuition is the same. One of the tricks to find the bottom of the bowl in fewer steps is to use not just the slope, but also curvature when deciding how big of a step to take. As the marble starts to roll down the
Okay, guys, here we are talking about gradient descent different technique. One of the first method, we call it gradient descent with the curvature. What do we mean by optimization? That we are to try to minimize or maximize certain reading. This is very important to machine learning. This is one of the used optimization within machine learning. For example, with regression model. So, as you see, exhaustive search, we measure all points in the curve. Then we find the minimum one. But this is, we are wasting time, we are wasting resources. We use a lot of computational cost. What do you mean by computational cost? Memory, processor, time, number of processes, complexity. So we are adding on top of those, which will make our model is a bit complex in terms of computation cost. Gradient descent is a good way because we are taking certain point. At the beginning, we take a point above and a point down. We calculate the slope depending on the slope. Then we will find where is the best thing or what is the best objective or that I will achieve my objective. So here we take it to the right of the curve and going down. So with curvature, now we are clarifying gradient descent with curvature, which is cheaper in matter of time, in matter of computation resources. I hope this is clear. Let's continue.
Side of the bowl, is the slope getting steeper? If so, then the bottom is probably still far away. Take a big step. Or is the slope getting shallower and starting to bottom out? If so, the bottom is probably getting closer. Take smaller steps now. Curvature, this slope of the slope, or Hessian, to give it its rightful name, can be very helpful if you're trying to take as few steps as possible. However, it can also be much more expensive to compute. This is a trade-off that comes up a lot in optimization. We end up choosing between the number of steps we have to take and how hard it is to compute where the next step should be. Like a lot of math problems, the more assumptions you're able to make, the better the solution you can come up with. Unfortunately, when working with real data, a lot of those assumptions don't always apply. There are a lot of ways that this drop a marble approach can fail. If there's more than one valley for a marble to roll into, we might miss the deepest one. Each of these little bowls or valleys is called a local minimum. We're interested in finding the global minimum, the deepest of all the bowls, the lowest of all the
Okay, here, one of the optimization target is to find a local minimum or a global minimum. What do you mean by those? He will clarify this in a few steps. Global minimum is the minimal point that will give me the minimum value of our objective function. Whatever. We are looking to the lowest, or to minimize, like to minimize the error in a classification, or to minimize the false alarm rate. We'll talk about those when we go deeper in the classification. So if we are looking to minimize, then the best optimization solution would be the global minimum, which is the minimum point over all other minimums. Local minimum at certain part or fraction of the curve, we can say this is the local minimum for these points. But for oval or the function, the minimum point would be the global minimum. I hope this is clear. Questions before we resume the video? Is there any question? Okay.
local minima. Imagine that we're testing our tea temperatures on a hot day. It may be that once the tea becomes cold enough, it makes a great iced tea, which is even more popular. But we could never find that out by gradient descent alone. Also, if the error function is not smooth, there are lots of places a marble could get stuck. This could happen if our tea drinker's enjoyment was heavily.
So here in this curve, this is a local minimum for this section. This is a local minimum. If we took like this section only from the beginning till here, this will be the local minimum, or this. But what is the global minimum? It is the lowest. But with this one, gradient descent is not performing well because we'll have a lot of points and we may reach, in worst case scenario, same as exhaustive optimization. Let's continue.
Impacted by passing trains, for instance. The periodic occurrence of trains could introduce a wiggle into our data. If the error function you're trying to optimize makes discrete jumps, that presents a challenge too. Marbles don't roll down stairs well. This could happen, for example, if our tea drinkers have to rate their enjoyment on a 10-point scale. If the error function is mostly a plateau, but has a bottom that's narrow and deep, then the marble is unlikely to find it. Perhaps our tea drinkers are very finicky and absolutely despise all tea that is anything but perfect. All of these occur in real machine learning optimization problems. If we suspect that our tea satisfaction curve has any of these tricky characteristics, we can always fall back to exhaustive search. Unfortunately, exhaustive search takes an extremely long time for a lot of problems. But luckily for us, there's a middle ground. There's a set of methods that's tougher than gradient descent. They go by names like genetic algorithms, evolutionary algorithms.
So here, guys, you will start hearing like evolutionary algorithm, heuristic, meta-heuristic, a lot of different type of optimization, but genetic algorithm till today is doing very, very, very well with some types, depending on the data set, with some types of machine learning techniques. That's why we will have a bit deeper talk about optimization before we start. This will put your leg on a solid ground of building machine learning problems and trying to solve it.
And simulated annealing. They take longer to compute and they take more steps, but they don't break nearly so easily. Each has its own quirks, but one characteristic that most of them share is a randomness to their steps and jumps. This helps them discover the deepest valleys of the error function, even when they're harder to find.
Here we are talking about the pros and cons of each technique. We are talking about gradient descent and exhaustive exploration, or what is called exhaustive search. So exhaustive search, we have fewer number of assumption, more assumption here in gradient descent. Here is robust because we are checking every single point. Here is sensitive because we are taking, depending if we talk the curvature, but if the curve like steps in 10 base graph, it would be a bit challenging, or if it is flat, then a drop, then back. So this would be more challenging to gradient descent. But this one as cons, expensive to compute, efficient to compute. One student yesterday, or in the last class, sorry, last week, asked me how the type of a question. So in this kind of a question, it would be true or false or multiple choice. We could use this information as part of our exam question. I'm giving you some hints here, guys. Let's continue.
Optimization algorithms that rely on gradient descent are kind of like Formula One race cars. They're extremely fast and efficient, but they require a very well-behaved track to work well, or error function to work well. A poorly placed speed bump can wreck it. The more robust methods are like four-wheel drive pickup trucks. They don't go nearly as fast, but they can handle a lot more variability in the terrain. And exhaustive search is like traveling on foot. You can get absolutely anywhere, but it may take you a really long time. They're each invaluable in different situations. Now that we've talked about how optimization works, click the link below to join me for part 2 of this series, where we step through an example of optimization in a machine learning model.
Okay, let us go to part 2.
Chasing that A and want to save time on proofreading? Grammarly makes editing one click simpler.
One way to think about machine learning is as a way to convert raw data to a simplified cartoon-like representation, a model, and to use that representation to make predictions and estimates. Whenever we're engaged in the first part, fitting a model to some data, there is some optimization going on. It's built into the foundation of machine learning. It comes to the foreground particularly when we're training deep neural networks. It's worth taking a look at a couple of examples of optimization in machine learning models. Let's start by looking at M&Ms. We'll use a model that's so simple we usually don't think of it as a model. We'll try to answer the question, how many M&Ms come in a bag? Finding an answer to this is easy. I bought a bag of M&Ms and I counted them and I ate them. The answer was 53 M&Ms in a bag. Then I bought a second bag. It had 57 M&Ms in it. Now I'm in a tight spot. If I answer 53, I'm only right half the time. If I answer 57, I'm still only right half the time. And if I answer 55, right in the middle of the two, I'm not right at all. There's no longer a right answer. It's like the situation described by the saying, a person with a watch always knows what time it is, but a person with 2 watches is never sure. Counting more bags of M&Ms didn't help the situation. The more I ate, the more I saw that there was no right answer. It became clear that being right was impossible. So I changed my goal to being less wrong. What's the least wrong estimate I can make about how many M&Ms come in a bag? This question I have a shot at answering. First, I had to make it very specific. I had to translate it to math. For a given guess and a given bag of M&Ms, the difference between them is D. If I number each bag of M&Ms, then the difference between my guess and the count of bag number 1 is D1. The difference between my guess and the count of bag number 2 is D2. The difference between my guess and the count of bag I is DI. D is often called the deviation. The next thing I need to decide is, if I'm off by a certain deviation, how much do I care? What's the cost to me? There are lots of valid ways to answer this question, and they all result in different answers. The most common is to take the deviation and square it. If a bag is twice as far as the estimate from another, it incurs 4 times the cost. This squared cost function cares more about the points that are way off than the ones that are close to correct. Another common cost function is absolute deviation. That way, if a bag is twice as far away from the estimate as another, it incurs just twice the cost. For some problems, this cost function makes the most sense. There are lots of other options. For instance, the square root of the deviation, or 10 raised to the power of the absolute value of the deviation, could also work. In all these cases, the cost goes up as the estimate gets further away from the actual count of the bag. For our purposes, we'll start with the squared deviation as our cost function. Calculating the total cost is straightforward. Another name for cost is loss, which comes with a cool curly L symbol, so we'll switch to that. The total loss for a given estimate can be calculated by adding up the cost associated with each bag. This is the square of the distance between the estimate and the number of M&Ms in that bag. In this form, we can calculate it. With a little Python code, we can run an exhaustive search on this problem and calculate the loss function for a wide range of estimates. There are links to all the code for this below. Feel free to check it out. Then all we have to do is pick off the M&M count that corresponds to the lowest value on the loss curve, the least wrong option. In this case, about 55.5 M&Ms. As you may or may not find interesting, there's another way to get at this estimate. Because this model is so simple, we can work out the math and find an analytic solution. There's going to be some lightweight calculus, so if that gives you the heebie-jeebies, feel free to skip to the next section. We're lucky to have a nice equation for the loss function. We know we're looking for the lowest point, and that this is the only place where the curve is flat, where it has a slope of 0. We can use this to solve for the estimate of n at this lowest point. We find the slope of the loss function with respect to the estimated number of M&Ms by taking its derivative, and then set that equal to 0 and solve it. We then just have to find the place where this is true, and that will show us our best estimate of n. We take advantage of the fact that the derivative of a sum is the sum of the derivatives of all its parts. Then we can take the derivative of each part. The exponent 2 comes down in front. Because the whole expression is already equal to 0, we can divide both sides by 2, then what's left is still equal to 0. And we can break out the sum into its pieces. We have a total of m bags of M&Ms. If we add up n estimated, m times, we end up with m times n estimated, multiplied. Then we can subtract this term from both sides and move it to the other side of the equal sign. And finally, we can divide by m. What we're left with is magically the sum of all the data values divided by the total number of data points. That is, the average of our counts. This unexpectedly slick result at the end of such a long path is one of the reasons optimization is so popular. Okay, calculus is over, back to the modeling discussion. Although it may not look like it, this is a model. It's a model of central tendency. It has all the hallmarks of a model. It's a simplified representation of our data. Instead of having to remember every single bag of M&Ms we counted, we created a single imaginary, but ideal, platonic, typical representative bag of M&Ms. It's like a cartoon in that it resembles the originals, but is far less complex. This is exactly what a model does. It also allows us to make predictions. If someone asks us how many M&Ms are in a bag that they're about to open, we can answer with confidence 55.48. We know that we're not correct. It's rare to find 0.48 of an M&M. But we know that our answer is less wrong than any other answer we could give. Although it was simple, this was a complete example of optimization for machine learning. Our model, central tendency, had a single parameter, the estimated number of M&Ms, that was adjusted to minimize a loss function. Most machine learning models have more parameters than this. Many layered neural networks can have millions of parameters, but the underlying process is similar. The number of all possible combinations of parameter values a model can have is called its parameter space. Exhaustive search requires visiting and evaluating every point in a model's parameter space, trying out every possible combination of parameter values. Because the central tendency model's parameter space was so small, we were able to get away with that, but it's not often the case that we can. It's also worth noting that the beautiful shortcut we found using the mean of the data points to find the optimal estimate via the mathematical long cut, the analytical derivation, is special. We can't expect to do such things or find such nice results most of the time. Being able to do that depends both on the simplicity of the model and on the exact choice of our loss function. For instance, if we had chosen absolute deviation loss rather than squared deviation loss, the mean is no longer the shortcut to get the best answer. In that case, it just so happens that the median is the right shortcut. But if we had chosen square root absolute deviation loss, I have no idea whether there would be any viable shortcut or what it would be. Most of the time, there will be no clean analytical solution and no shortcut for calculating optimal parameter values. We'll have to find them using gradient descent or some slower but tougher method. This example showed how optimization works in a single parameter machine learning model. Click the link below to join me for part 3, where we use optimization to fit a 2-parameter model.
Hey, I am Harsh Moore. I am a full-stack developer based out of New Delhi, the capital of India.
In part 2, our measure of central tendency for M&M weight was a single parameter model. There was just one number we could adjust to change the result. Just one slider to slide, just one knob to turn. Let's take a look at how this works with a 2-parameter model. Let's consider another set of M&M data points. This time around, we carefully weighed the bag before opening it and counting the M&Ms inside. We can represent the counts and weights of each bag in a 2-dimensional plot. This scatter plot shows all the bags we ate. There's a clear pattern here. Visually, you can draw a diagonal line right through the middle of these points. This makes sense when you consider how very uniform in size M&Ms are. We're talking about the plain ones, not the peanut ones. If all M&Ms had exactly the same weight, as did their paper packaging, these points would lie perfectly on the same straight line. But since there's some variation, that introduces a bit of scatter. Because this appears so linear, let's fit a straight line model to it. The equation of a line is the y value is equal to the x value times the slope plus the y-intercept. For this data, x is the M&M count and y is the bag weight. The slope and the intercept are now our 2 parameters, our 2 dials that we get to adjust to improve the fit of our model. For convenience, we'll continue to use our squared deviation as our cost function. It just so happens that when fitting a line with a squared deviation cost function, there is another very elegant analytic solution for the best parameters, just like there was for central tendency, when we learned that we could jump straight to it by calculating the mean. However, we'll ignore that analytic solution for our straight line for now, so that we can play with 2-parameter optimization. We have the luxury, once again, of being able to do an exhaustive search. This gives us a bird's eye view of how the loss function varies across the parameter space. Looking at the loss function, we see that for this particular model and data, it is not so much a bowl as it is a narrow valley that's slightly deeper in the middle. It looks like a bowl that's been squished sideways. The plateau on top is not actually part of the loss function, It's just where we chopped it so that we could focus on the valley, which is the most interesting bit. The loss function continues to get higher and steeper the farther it gets away from the bottom of that valley. We're going to bypass the second obvious solution to this problem, which is just to choose the lowest point out of all of them. We're going to pretend for now that we don't know where that lowest point is. Instead, we'll start by picking an arbitrary point in the parameter space. It corresponds to a single value of the slope and intercept, and there's one particular line that it corresponds to. We can show that together with our data points. Then we can adjust one of our dials. We can shift the intercept up and down. Notice that as the line passes through the data points, the loss gets lower, and once the line moves past the data points, the loss climbs again. There's a point in the middle at which it's quite low, but that's still not quite the lowest value of the loss function across the entire parameter space. We can change gears and play with the second parameter, the slope. This corresponds to moving in a different direction in the parameter space. In our model, it results in wiggling the line back and forth. And again, we see that depending on the value of the slope, the value of the loss function goes up and down, but it never quite reaches the bottom, its lowest possible value. It's possible to move both parameters at once. Again, we see that the value of the loss function jumps up and down, tracking the combination of parameter values we've chosen. At this point, it's probably clear what needs to happen. Our point in parameter space needs to roll down to the bottom of the bowl until it finds the deepest part. This is exactly what gradient descent does for us. We can start off way up high and make a step headed down the hill, with the size of the step being related to the steepness of the slope. This moves us closer to the bottom of the valley, but doesn't get us there yet, so we repeat it, stepping down the slope, whichever direction that is, again and again, with the step size related to the steepness. Then, finally, we're there. We have found the best pair of parameters. The best fitting offset is 4.2, and the best fitting slope is 0.915. It's worth noting that the offset in our model is the weight of the paper packaging. It's the weight of the package when the M&M count is 0, or when X is 0. And the slope is the change in weight when the count increases by 1, the weight of a single M&M. Looking at our linear fit example, we can start to see how optimization works when used with more complicated models. Click the link below to join me for the fourth and final part of this series, where we show how optimization extends to many parameter models, including deep neural networks.
You might have
Now that we've laid all the groundwork, we can take things up a level and see how to apply optimization in a 3-parameter model by looking at another M&M dataset. We noticed when fitting our line that not every bag had identical M&M weights. Some of them were noticeably higher and some noticeably lower than others. We suspect there might be an underlying pattern here, and our suspicions are further aroused when we talk to some of our friends that work at the M&M factory. We learned that they upgraded their equipment during the period that our M&Ms were being sampled from, but we don't know exactly when. If there was a change in M&M weight due to the change in equipment, we would expect to see a jump at some point, with the M&Ms coming after the jump, having a consistently higher or lower weight. When we plot the average M&M weight in a package against the manufacturing date of that package, we see that there probably is a small difference. There are 3 questions this data could help us answer. What was the typical M&M weight before the change? What was the typical M&M weight after the change? And when did the change occur? There are lots of generic models available. These are models like linear regression or decision trees that don't know anything about where our data came from or what it means or how we got it. In this example, we can do a little bit better than these naive models. We have some extra information that helps us to make a better guess at what our model should look like. Given what we know, it's reasonable to hypothesize a model with a constant M&M weight before and after the equipment change, and a step change between them. This is a 3-parameter model. There's 3 numbers we need to define it completely: the weight before the change, the weight after, and the date of the change. For consistency, we'll keep our loss function as the square of the deviation between our model and the data. We can now perform an exhaustive search again over all possible combinations of all plausible parameter values, but notice that it's taking a lot longer to compute with each additional parameter. And we can get a 4-dimensional loss function. Plotting a 3-dimensional function is tricky, but plotting a 4-dimensional function is really hard. But we'll give it a try. One trick we can use is to choose a specific value for one of our parameters. What's left is a 3-dimensional loss function. This lets us experiment and get a feel for how those 2 parameters interact, where the sweet spot is for both of them, and then we can see, at least for this value of the 3rd parameter, what combination of the other 2 parameters produces the lowest loss. In our case, we have fixed the day on which the equipment was swapped out and are varying the other 2 parameters: the weight of an M&M before the change and the weight of an M&M after. The loss function helps us see what the best estimates are for these, at least if we assume this particular equipment shift day. Another trick we can use is to take the parameter that we chose a fixed value for, our shift day, and increment it just a little bit. We can do this again and again and get a series of 3-dimensional plots. What this does is to take one of our dimensions and spread it out across time. We can use time to represent our 4th dimension. If you look very carefully as the shift day progresses through its values, you can see the bottom of our bowl jump up and down. This shows how the lowest possible value for the loss function changes depending on the shift day. We're looking for the very lowest of all possible values. That is the optimal estimate. It depends not only on our estimate of M&M weight before and after the shift day, but also on our choice of the shift day. There are 3 separate choices we have to make, 3 separate dials we have to spin to find the best answer. If you watch the bottom of the bowl very carefully as the shift day progresses, you can see that it reaches a low point, then jumps back up again, then reaches another low point. This means that gradient descent will give us different answers depending on where we start. The answer is sensitive to our initial guess. This is an example of non-convex loss function. As we mentioned before, there are a few ways to handle this. We won't go into them in detail here, but one method that's good to have in your bag of tricks is a scattershot approach. That involves choosing several random starting points and running gradient descent from each of them. Once you discover that several of them are ending up in the same place, or that several of them are giving the same minimum value, then you can be reasonably confident that you have a good answer. The more random starting points you pick, and the more times you choose a random starting point and try again, the better your chances of finding the global optimum. Although you'll never be able to guarantee that you have the absolute best answer. It's worth keeping in mind, however, that in machine learning applications, we are dealing with data that's assumed to have some noise on it, and that we'll be applying our model to future data points that will have their own unique patterns of noise in them. It's not worth our time to worry about getting the exact, perfect global optimum. For our purposes, getting an answer that is just as good as we can get is usually good enough. This one concept of looking for the lowest point in an error function is all you need to survive in optimization for machine learning. It takes a lot of different forms, can extend to many more parameters. It can be used with generic models like logistic regression, where there are just a few parameters or a few dozen of them. It can be used with very domain-specific models, such as macroeconomics or agriculture. The optimization method doesn't know the difference. In either case, all it does is tries to find the right combination of values for getting the lowest loss. Optimization is also at the heart of deep neural networks' success. It's how all of the weights, making all of the between-layer connections from node to node, are chosen. In these models, there can be thousands or even millions of parameters. The loss function is not only impossible to draw on a sheet of paper, it's mind-boggling to even contemplate. But the math behind optimization carries on anyway, doing its thing and seeking out the lowest points of the loss function that it can find. A quirky thing about optimization in deep neural networks is that the loss function is known to have many dips, like a many-dimensional egg crate mattress. Depending on where you drop a marble, it will very likely land in a different divot every time. Deep neural networks can take a long time to train, and in practice, they are often trained only once, starting from a single random set of initial weights. That means that of all the millions of low points available in the loss function, we are only going to find one. This may be one of the reasons that training neural networks is such an art. It's not quite as bleak as it sounds, however. Some recent research suggests that most of these divots have the same depth, like an actual egg crate mattress, at least for certain types of neural networks. So maybe the multitude of local minima is not as much of an issue as it might appear at first glance. Another part to the art of deep neural networks is the alphabet soup of gradient descent methods. As you read about it, you'll hear names like SGD, stochastic gradient descent, NAG, Nesterov accelerated gradient, ATOM, or ADAGRAD. All of these are embellishments of gradient descent. They differ in the fine details about exactly how far to step and in precisely which direction. Some work a little better for some problems than others. But mostly they just change how fast the neural network converges to the final answer. In every case, the underlying goal is the same. Starting from a random place in a many-dimensional landscape of hills and valleys, find the lowest point in the nearest valley going downhill. The other type of optimization that occurs in deep neural networks is hyperparameter tuning. This is still just optimization, but instead of optimizing the many parameters in the model, it's actually optimizing the values of some of the high-level settings that determine how the model works. In some cases, determining how gradient descent is performed. If decorating a house, you can think of model training as optimization, where you're choosing exactly where within a room the couch and the bookshelf and the picture should be and how they should be oriented. Hyperparameter tuning is the next level up. It's deciding which room they should even be in to start with. Because testing a new set of hyperparameter values requires retraining the model entirely from scratch, it takes a long time and usually a lot of computers. Computational intensity has driven creative machine learning practitioners to find ways to try as few hyperparameter combinations as possible. However, the underlying goal and the underlying problem are still the same. Find the combination of values that gives the lowest loss. Get to the bottom of the deepest valley you can find. Great job sticking in there to the end. Thanks for hanging in there with me. I hope the concept of optimization is a little bit less scary now, and that you have an intuitive sense of what's going on under the hood when the machine learning algorithm is being trained. Good luck on building your next project.
Okay, guys, I hope this gives you why machine learning is depending, or why optimization is very important in machine learning. Now we will start having some videos about convex versus non-convex gradient descent based optimization. We will have this video. By the way, I already added to the resources all 4 videos links in OWL, in addition to the previous class videos that we watched. So now we'll have another video talking about convex versus non-convex optimization, and we'll go from there. We still have another 3 videos to watch. Let me share my screen again.
Hello, welcome to the machine learning course. So today we will discuss on optimization in machine learning and deep learning model. So basically I will discuss the following topics in this video, and is why optimization is required in machine learning, what is convex and what is non-convex functions or objective functions, what is gradient based optimizations, and what is the status of optimization in deep learning architecture. Okay. The goal of machine learning and deep learning is to reduce the difference between the predicted output and the actual output, and this is also called a cost function and a loss function. So the basic concept is that for every training instance you compute the predicted output. Okay, you predict the output and then you find out a difference or some loss between this predicted output and this ground truth, and this difference is called a loss function. It could be anything. For regression it sometimes it is usually the square error, and for classification it is cross entropy loss usually considered. We know that, right? And then how we compute the cost function? You just sum it over all the training examples, and then you take the average by taking the total number of samples in training instances in your training set. And since your predicted output is a function of the model parameters, suppose the weight vector and the bias, so your cost function will be also a function of this weight and bias. And the objective of your training algorithm is to find out a optimal value of this weight and bias for which this cost function, this value of the cost function will be minimum. And because that's why then only we will get a optimal model which will always give us the minimum error when we predict some new instances, right? Predict the output for some new instances. And so for some very few machine learning algorithms such as linear regression, we can find out this optimal value of this W and B, suppose this model parameters W star and B star, suppose they are optimal values. We can compute them by using closed form equation, that is also called normal equation, and by using the SVD method approach, that is also called singular value decomposition approach. And that is an exceptional case for linear regression only, where we can find the closed form, we can use the closed form equation to find out the optimal parameters. But in most of the cases, most of the machine learning models will not get any closed loop equation. Okay, so we cannot find out mathematically just using an equation what is the optimal parameter for a cost function. Okay, so what is the solution? The solution is very simple. The solution is to employ the optimization algorithm. Okay, and so with this, let's dig into how, let's see what is lies beneath the training of a machine learning algorithm. But when in practice, when you use machine learning for any project, usually you don't bother about much about what is the optimization algorithm, okay, that is running beneath the machine learning model, because scikit-learn ML model will generally not require you to actually know the stuff how this optimization actually occurs, but maybe just set some tuning parameters. It takes care of the rest. Okay, so for example, if you train a SVM without knowing any mathematics in scikit-learn, you just feed the data, you just set some parameter, what is the kernel type, and move on. Okay, and rest of the things will be taken care of the scikit-learn library. Okay, and similar things is also applicable for TensorFlow models or using other libraries like PyTorch or Keras. Okay, so that being said, knowing some basic optimization can be helpful in algorithm or problem design and analysis, especially if you are working on some theory stuff, some hardcore theory stuff in machine learning, or implementing some optimization algorithms yourself. Okay, so it's better to know something what is under the hood. Okay, so let's see what is lies beneath the training of a machine learning algorithm. So first of all, we have to define a cost function. Okay, we have to define a cost function. So let's see that what is the anatomy of a learning algorithm. Okay, so first of all, we have to define a cost function or error function. Then we have to select the optimization criteria based on that loss function. And thirdly, we have to set a optimization routine that leverages the training data to find a solution to the optimization criteria. Okay, so this cost function, also called the objective function of the optimization algorithm. Okay, so let's see what we mean by optimization in general. Okay, so optimization is basically refers to the task of either minimizing or maximizing some function effects like this, or it can be anything. Suppose this is a one-dimensional function with independent variable x. Okay, so the optimization means either minimizing or maximizing this function fx by varying this independent variable x, and you have to find out this minima or maxima. But in general, we suppose in this context we will discuss the minimization thing. Okay, so we will find out a x for which this function, this value of this function of will be minimum. Okay, and this is mathematically defined with this way: this x star equal to argument minimum of fx. Oh, so we usually phrase most optimization problem in terms of minimizing fx, or in the other way around, you can say that maximization may be accomplished by a minimization algorithm by minimizing the minus of fx. Okay, so minimizing fx means maximizing minus of fx. Okay, so this is a one-dimensional function. So simply we can plot a two-dimensional function also. Okay, so that is f of xy, and that would be if we plot the landscape in a surface, then we'll see like this. It is a nonlinear surface, highly nonlinear surface, and so its landscape will be like this. So okay, and if in machine learning this cost function or objective function will be with many higher dimension. It will have many higher dimension because your system, your model will be having so many parameters, and that would be function of so many parameters, and that would be a function of basically your weight matrix and the bias, right? And there are so many parameters, so it would be much more complex. Okay, so it's just an example of two-dimensional loss function. Now let's see one of the most important or popular optimization algorithm in machine learning, that is called gradient based optimization. So if you read the modern literature on machine learning, you will see that you often encounter the reference to gradient descent or stochastic gradient descent. And these are two most frequently used optimization algorithms used in cases where the optimization criteria is differentiable. Optimization criteria means your objective function is differential. Your cost function will be differentiable. Okay. So gradient descent is an iterative optimization algorithm for finding the minimum of a function. And to find a local minimum of a function using gradient descent, you have to start from some random point like this. You will just start from a random point like this, and then you take steps proportional to the negative of the gradient or approximate gradient of the function at the current point. So you will just take the smaller steps towards the minimum, and you will find the minimum this way. And this is the basic essence of gradient based optimization, because in every step you are going towards the minimum. Okay, so now in gradient descent, the most important parameter is the learning rate, that is the step size. So most important parameter in gradient descent is the size of the steps determined by the learning rate hyperparameter. And if the learning rate is too small, then what will happen? Then the algorithm will have to go through many iterations to converge to the minimum, right? So if your learning rate is very small, what will happen? It will take many more steps to converge to the minimum. And so you will need many number of iterations to converge, and which will take a enormous amount of time. Okay, and which is not desirable. And on the other hand, what can happen is that if the learning rate is too high, then what will happen? If learning rate is too high, you might jump across a valley and you may end up on the other side. You may start from here, and then you may start from here, and then you could jump here, and then again you could jump here, then again you could jump here, and you will just eventually it will jump back and forth around the global minimum, and you will not find the global optima at all. Although if you If you run it for a very longer time, then also you will not find a optimal solutions because your learning rate is not properly chosen. So learning rate is a very important thing in gradient descent algorithm. Okay. The gradient descent is an optimization algorithm, and you can apply this optimization algorithm to any type of objective function, and the shape of the objective function could be of any type. It could be like this, it could be like this, or anything. Now the question is that, can the gradient descent be used to find the optimal parameters for any function? And the answer of this question is that no, not necessarily. The gradient descent is guaranteed to find the global minimum if and only if your objective function is convex in nature. Okay. So gradient descent will...
Okay, guys, here it's showing that gradient descent is your best solution if you have a convex cost function. What do you mean by convex cost function? How it will be the best? Concentrate on the following part of the presentation.
will find the global minimum if the learning rate is properly chosen and if wait for long enough. That means you will run it for more number of iterations, and if your learning rate is properly chosen and your objective function is convex in nature, then only it will find the global minima. Okay, so gradient descent can only find the optimal parameters for any convex objective function, for not all objective function. Now obviously the question comes, the basic question comes, what do you mean by object or convex function? Okay, so convex function can be very easily defined. That convex function, which means that if you pick any 2 points on the curve, okay, and the line segment joining them, suppose I pick this 2 curve and line segment joining them never cross the curve. Okay, you can choose any 2 curve, okay, any 2 curve like this, and it will not cross the curve again. So if your objective function is like this and you will choose any 2 curve, and you will see that it is not, this curve is this line segment joining them is not intersecting the curve again. Okay, so this is called convex function. This type of function is called convex function. Mathematically we can express that in different way, but I'm not going into that thing, but the simple thing is that. And another definition also you should know that what is convex function. Convex function is that your local minima is local minima equal to your global minima. So for convex function, the local minima equal to global minima. Okay, so this is the basic definition of convex function. So let's see another type of convex function. So both are convex function. Okay, but this is not a convex function. This is a non-convex function. Okay, so for non-convex function, you could have different minima. You could have numerous minima along the signal dimension or function dimension, and you will have different minima, and one will be different local minima, but there will be one global minima. Okay, usually. So for non-convex function, your local minima is not necessarily equal to a global minima. Okay. Now let's see what will happen if we apply gradient descent to a non-convex objective function like this. So this is a non-convex objective function. So what will happen, you will start, you are supposed to find this global minimum, but you are not guaranteed, it is not guaranteed that you will find this global minimum. You may stuck at a local minimum, right? Because this is an iterative algorithm, and you may start from this side and you may get stuck at this local minimum. Okay. Or you might have some plateaus like this where your learning rate, thus you apply same learning rate and you will not even go to this global minima if you start from this point, if your learning rate is too small. So there is no guarantee. Okay, so you run it for so many iterations that whether you will find this global minima or not, there is no guarantee. So that is the problem of gradient descent algorithm. If you apply this on non-convex function, there is no guarantee that you will find the global minimum. Okay. So optimization algorithms like this gradient descent, may fail to find the global minima when there are multiple local minima like this. And in the ideally you want to find this global minima, but you may end up in a local minima, and you will think that this is my global minima, and you just think that it is a non-optimized model. You will end up with a non-optimized model. Okay, so back to our machine learning algorithms and their corresponding objective functions. So in traditional machine learning models such as linear regression, logistic regressions, or SVM, we can see that all the good news about this objective objective function is that all these objective functions are convex in nature. So we can apply the gradient descent algorithms to find the optimal model parameter, right? So you can see that. So basically we have formulated that. So the result of the optimization algorithms are your model parameters up to training. Okay, so we can find out, we can apply the gradient descent and we can find out the optimal parameters for their objective function because they are all convex objective function, and we know that the gradient descent will find the global minima if the objective function is convex in nature, right? So usually for linear regression, logistic regression, and all this machine learning algorithm, the gradient descent is applied. But for SVM, the kernelized SVM or linear SVM, this is convex optimization function but with some constraint. So these are all constraint optimization function, objective function, and the constraint convex objective function, if we apply gradient descent, that would be very slow. So that's why some different methods is used, that is called quadratic programming based optimization function, quadratic programming based solver or optimization algorithms. So QP, the quadratic programming, is used to find the solution of the kernelized SVM and linear SVM. But you can apply gradient descent on the linear SVM, but that would be very slow compared to the quadratic programming based optimization. So it is better to use quadratic programming based optimization on constant objective function. So with this I am going to stop this video. In the next lecture I will discuss the optimization in the context of deep neural network, and I will discuss how we can express the objective function in the context of deep neural network and how optimization can be applied. So thank you for watching. Thank you.
Okay, here we'll dig more in gradient descent. This video.
Oxford is like a new experience, it's like a new world. It's
Hi, with this video I will explain how gradient descent works, and for this purpose I will use a very simple example. First of all, we need to know what is gradient descent. It is an optimization algorithm to find the minimum of function. We start with a random point on the function and move in the negative direction of the gradient to the function to reach the local or global minimum. Let's start with example. We have a function I equal x plus 5 in square. And step number 1 is to choose a random point, and let's say the first random point in our example is x equal minus 3. And then we have to find the gradient of the function. And the gradient of the function is a derivative of the function. And it equal to 2 multiplied by x plus 5 in brackets. It is a very simple function, so we can calculate the derivative of this function just by moving the degree of argument to the beginning between brackets, and we have 2 multiplied by x plus 5, and this is a gradient of the function. Step number 2, and in this step we have to move in the direction of the negative of the gradient. But how much to move? For that we have to define a learning rate. In our example, learning rate is 0.01. Step number 3. In this example, we perform 2 iterations of gradient descent for understanding the logic of how gradient descent works. Let's begin with initialization of parameters. We have x0 equal to minus 3. We have a gradient function is 2 multiplied by x plus 5 in brackets, and we have a learning rate is equal 1. Let's start with the first iteration. We have x1 equal to x0 minus learning rate multiplied by gradient. Put the values in correct places. We have a function like this: minus 3 from x0 minus 0.01 is learning rate multiplied by 2 multiplied by the gradient is minus 3 plus 5. This is a random point, this is a learning rate, and this is a derivative or gradient of the function. And we have a result minus 3.04. When we choose learning rate 0.01, we move in the opposite direction by this step, and we have the next value in x-axis equal to 3.04. Iteration number 2. For iteration number 2, we have to perform totally the same action as we did in iteration number 1. So we have a function x2, this is the second point in x-axis, equal to x1. In the first iteration it was x0. Now we have to put x1 minus learning rate multiplied by the gradient. Put the values in the correct places, and we have x1 equal to minus 3.04 from the first iteration minus learning rate is 0.01 multiplied by 2 multiplied by minus 3.04 plus 5. We have the second point in the x-axis by step of 0.01, and we have minus 3.0792. This is the next point from the second iteration. In order to reach global minimum, we must perform more iterations, and we have to perform exactly the same action for each iteration to get more values on x-axis till we reach global or local minimum. In this example, we have a global minimum x equal -5. Thank you for watching this video. I hope that it is useful.
Okay, you see here, guys, that the function is convex. What is the convex function again? A convex function that if I have a line between each 2 points, it will not cross the curve again. What does that mean? If we have a function in this way, if I make between these 2 points, I will intersect the function again. But with convex, whatever it is, like V shape, U shape, once I draw a line between any 2 points in the curve, I will not intersect the function graph again. And as we said, convex, the global minimum is equal to local minimum. And I have only one global minimum in convex function. Here you see that gradient descent perform very well with such kind of function curves. Questions before we watch the last video? Again, it will repeat the gradient descent. Why we watch all this amount of videos about a gradient descent? Because I want everybody to be aware, what do we mean when we're talking about a gradient descent? What is the objective function? What is the learning rate, to be clear for all of you?
Oxford Summer Courses, educating young people from all over the world.
Gradient descent is decent at estimating parameters. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to learn about gradient descent and we're going to go through the algorithm step by step. Note, this StatQuest assumes you already understand the basics of least squares and linear regression, so if you're not already down with that, check out the quest. In statistics, machine learning, and other data science fields, we optimize a lot of stuff. When we fit a line with linear regression, we optimize the intercept and the slope. When we use logistic regression, we optimize a squiggle. And when we use t-SNE, we optimize clusters. These are just a few examples of the stuff we optimize. There are tons more. The cool thing is that gradient descent can optimize all these things and much more. So if we learn how to optimize this line using gradient descent, then we'll have learned the strategy that optimizes this squiggle, and these clusters, and many more of the optimization problems we have in statistics, machine learning, and data science. So let's start with a simple data set. On the x-axis, we have weight. On the y-axis, we have height. If we fit a line to the data, and someone tells us that they weigh 1.5, we can use the line to predict that they will be 1.9 tall. So let's learn how gradient descent can fit a line to data by finding the optimal values for the intercept and the slope. Actually, we'll start by using gradient descent to find the intercept. Then, once we understand how gradient descent works, we'll use it to solve for the intercept and the slope. So for now, let's just plug in the least squares estimate for the slope, 0.64. And we'll use gradient descent to find the optimal value for the intercept. The first thing we do is pick a random value for the intercept. This is just an initial guess that gives gradient descent something to improve upon. In this case, we'll use 0, but any number will do. And that gives us the equation for this line. In this example, we will evaluate how well this line fits the data with the sum of the squared residuals. Note, in machine learning lingo, the sum of the squared residuals is a type of loss function. We'll talk more about loss functions towards the end of the video. We'll start by calculating this residual. This data point represents a person with weight 0.5 and height 1.4. We get the predicted height, the point on the line, by plugging weight equals 0.5 into the equation for the line. And the predicted height is 0.32. The residual is the difference between the observed height and the predicted height. So we calculate the difference between 1.4 and 0.32. And that gives us 1.1 for the residual. We'll keep track of the sum of the squared residuals up here. Here's the square of the first residual. The second residual is 0.4. And the third residual is 1.3. In the end, 3.1 is the sum of the squared residuals. Now, just for fun, we can plot that value on a graph. This graph has the sum of squared residuals on the y-axis and different values for the intercept on the x-axis. This point represents the sum of the squared residuals when the intercept equals 0. However, if the intercept equals 0.25, then we would get this point on the graph. And if the intercept equals 0.5, then we would get this point. And for increasing values for the intercept, we get these points. Of the points that we calculated for the graph, this one has the lowest sum of squared residuals. But is it the best we can do? What if the best value for the intercept is somewhere between these values? A slow and painful method for finding the minimal sum of the squared residuals is to plug and chug a bunch more values for the intercept. Ugh. Don't despair. Gradient descent is way more efficient. Gradient descent only does a few calculations far from the optimal solution and increases the number of calculations closer to the optimal value. In other words, gradient descent identifies the optimal value by taking big steps when it is far away and baby steps when it is close. So let's get back to using gradient descent to find the optimal value for the intercept, starting from a random value. In this case, the random value was 0. When we calculated the sum of the squared residuals, the first residual was the difference between the observed height, which was 1.4, and the predicted height, which came from the equation for this line. So we replaced predicted height with the equation for the line. Since the individual weighs 0.5, we replace weight with 0.5. So for this individual, this is their observed height, and this is their predicted height. Note, we can now plug in any value for the intercept and get a new predicted height. Now let's focus on the second data point. Just like before, the residual is the difference between the observed height, which is 1.9, and the predicted height, which comes from the equation for the line. And since this individual weighs 2.3, we replace weight with 2.3. Now let's focus on the last person. Again, the residual is the difference between the observed height, which is 3.2, and the predicted height, which comes from the equation for the line. And since this person weighs 2.9, we'll replace weight with 2.9. Now we can easily plug in any value for the intercept and get the sum of the squared residuals. Thus, we now have an equation for this curve, and we can take the derivative of this function and determine the slope at any value for the intercept. So let's take the derivative of the sum of the squared residuals with respect to the intercept. The derivative of the sum of the squared residuals with respect to the intercept equals the derivative of the first part plus the derivative of the second part plus the derivative of the third part. Let's start by taking the derivative of the first part. First, we'll move this part of the equation up here so that we have room to work. To take the derivative of this, we need to apply the chain rule. So we start by moving the square to the front and multiply that by the derivative of the stuff inside the parentheses. Boop, boop, beep, boop, 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 boop. These parts don't contain a term for the intercept, so they go away. Beep, boop. Then we simplify by multiplying 2 by -1. And this is the derivative of the first part. So we plug it in. Now we need to take the derivative of the next two parts. I'll leave that as an exercise for the viewer. Bam! Let's move the derivative up here so that it's not taking up half the screen. Now that we have the derivative, gradient descent will use it to find where the sum of squared residuals is lowest. Note, if we were using least squares to solve for the optimal value for the intercept, we would simply find where the slope of the curve equals 0. In contrast, gradient descent finds the minimum value by taking steps from an initial guess until it reaches the best value. This makes gradient descent very useful when it is not possible to solve for where the derivative equals 0, and this is why gradient descent can be used in so many different situations. Bam! Remember, we started by setting the intercept to a random number. In this case, that was 0. So we plug 0 into the derivative, and we get -5.7. So when the intercept equals 0, the slope of the curve equals -5.7. Note, the closer we get to the optimal value for the intercept, the closer the slope of the curve gets to 0. This means that when the slope of the curve is close to 0, then we should take baby steps because we are close to the optimal value. And when the slope is far from 0, then we should take big steps because we are far from the optimal value. However, if we take a super huge step, then we would increase the sum of the squared residuals. So the size of the step should be related to the slope, since it tells us if we should take a baby step or a big step, but we need to make sure the big step is not too big. Gradient descent determines the step size by multiplying the slope by a small number called the learning rate. Note, we'll talk more about learning rates later. When the intercept equals 0, the step size equals -5.7. With the step size, we can calculate a new intercept. The new intercept is the old intercept minus the step size. So we plug in the numbers, and the new intercept equals 0.57. Bam! In one big step, we moved much closer to the optimal value for the intercept. Going back to the original data and the original line, with the intercept equals 0, we can see how much the residuals shrink when the intercept equals 0.57. Now let's take another step closer to the optimal value for the intercept. To take another step, we go back to the derivative and plug in the new intercept. And that tells us the slope of the curve equals -2.3. Now let's calculate the step size. By plugging in -2.3 for the slope and 0.1 for the learning rate. Ultimately, the step size is -2.3, and the new intercept equals 0.8. Now we can compare the residuals when the intercept equals 0.57 to when the intercept equals 0.8. Overall, the sum of the squared residuals is getting smaller. Notice that the first step was relatively large compared to the second step. Now let's calculate the derivative at the new intercept, and we get -0.9. The step size equals -0.09, and the new intercept equals 0.89. Now we increase the intercept from 0.8 to 0.89. Then we take another step and the new intercept equals 0.92. And then we take another step and the new intercept equals 0.94. And then we take another step and the new intercept equals 0.95. Notice how each step gets smaller and smaller the closer we get to the bottom of the curve. After 6 steps, the gradient descent estimate for the intercept is 0.95. Note, the least squares estimate for the intercept is also 0.95. So we know that gradient descent has done its job, but without comparing its solution to a gold standard, how does gradient descent know to stop taking steps? Gradient descent stops when the step size is very close to 0. The step size will be very close to 0 when the slope is very close to 0. In practice, the minimum step size equals 0.001 or smaller. So if this slope equals 0.009, then we would plug in 0.009 for the slope and 0.1 for the learning rate, and get 0.0009, which is smaller than 0.001, so gradient descent would stop. That said, gradient descent also includes a limit on the number of steps it will take before giving up. In practice, the maximum number of steps equals 1,000 or greater. So, even if the step size is large, if there have been more than the maximum number of steps, gradient descent will stop. Okay, let's review what we've learned so far. The first thing we did is decide to use the sum of the squared residuals as the loss function to evaluate how well a line fits the data. Then we took the derivative of the sum of the squared residuals. In other words, we took the derivative of the loss function. Then we picked a random value for the intercept. In this case, we set the intercept to be equal to 0. Then we calculated the derivative when the intercept equals 0, plugged that slope into the step size calculation, and then calculated the new intercept, the difference between the old intercept and the step size. Lastly, we plugged the new intercept into the derivative and repeated everything until step size was close to 0. Double bam! Now that we understand how gradient descent can calculate the intercept, let's talk about how to estimate the intercept and the slope. Just like before, we'll use the sum of the squared residuals as the loss function. This is a 3D graph of the loss function for the different values for the intercept and the slope. This axis is the sum of the squared residuals. This axis represents different values for the slope, and this axis represents different values for the intercept. We want to find the values for the intercept and slope that give us the minimum sum of the squared residuals. So, just like before, we need to take the derivative of this function. And just like before, we'll take the derivative with respect to the intercept. But unlike before, we'll also take the derivative with respect to the slope. We'll start by taking the derivative with respect to the intercept. Just like before, we'll take the derivative of each part. And just like before, we'll use the chain rule and move the square to the front and multiply that by the derivative of the stuff inside the parentheses. Boop, 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 boop. Since we are taking the derivative with respect to the intercept, we treat the slope like a constant, and the derivative of a constant is 0. So we end up with -1, just like before. Beep boop. Then we simplify by multiplying 2 by -1. And this is the derivative of the first part. So we plug it in. Likewise, we replace these terms with their derivatives. So this whole thing is the derivative of the sum of squared residuals with respect to the intercept. Now let's take the derivative of the sum of the squared residuals with respect to the slope. Just like before, we take the derivative of each part. And just like before, we'll use the chain rule to move the square to the front and multiply that by the derivative of the stuff inside the parentheses. Beep, beep, boop, boop, boop. Since we are taking the derivative with respect to the slope, we treat the intercept like a constant, and the derivative of a constant is 0. So we end up with negative 0.5. Boop, boop. Then we simplify by moving the negative 0.5 to the front. Note, I left the 0.5 in bold instead of multiplying it by 2 to remind us that 0.5 is the weight for the first sample. And this is the derivative of the first part. So we plug it in. Likewise, we replace these terms with their derivatives. Again, 2.3 and 2.9 are in bold to remind us that they are the weights of the second and third samples. Here's the derivative of the sum of the squared residuals with respect to the intercept, and here's the derivative with respect to the slope. Note, when you have two or more derivatives of the same function, they are called a gradient. We will use this gradient to descend to the lowest point in the loss function, which, in this case, is the sum of the squared residuals. Thus, this is why the algorithm is called gradient descent. Bam! Just like before, we'll start by picking a random number for the intercept. In this case, we'll set the intercept to be equal to 0. And we'll pick a random number for the slope. In this case, we'll set the slope to be 1. Thus, this line, with intercept equals 0 and slope equals 1, is where we will start. Now let's plug in 0 for the intercept and 1 for the slope. And that gives us two slopes. Now we plug the slopes into the step size formulas and multiply by the learning rate, which this time we set to 0.01. Note, the larger learning rate that we used in the first example doesn't work this time. Even after a bunch of steps, gradient descent doesn't arrive at the correct answer. This means that gradient descent can be very sensitive to the learning rate. The good news is that in practice, a reasonable learning rate can be determined automatically by starting large and getting smaller with each step. So, in theory, you shouldn't have to worry too much about the learning rate. Anyway, we do the math and get two step sizes. Now we calculate the new intercept and new slope by plugging in the old intercept and the old slope and the step sizes. And we end up with a new intercept and a new slope. This is the line we started with, and this is the new line after the first step. Now we just repeat what we did until all of the step sizes are very small or we reach the maximum number of steps. This is the best fitting line with intercept equals 0.95 and slope equals 0.64, the same values we get from least squares. Double bam! We now know how gradient descent optimizes two parameters, the slope and the intercept. If we had more parameters, then we just take more derivatives and everything else stays the same. Triple bam! Note, the sum of the squared residuals is just one type of loss function. However, there are tons of other loss functions that work with other types of data. Regardless of which loss function you use, gradient descent works the same way. Step 1. Take the derivative of the loss function for each parameter in it. In fancy machine learning lingo, take the gradient of the loss function. Step 2. Pick random values for the parameters. Step 3. Plug the parameter values into the derivatives. The gradient. Step 4. Calculate the step sizes. Step 5. Calculate the new parameters. Now go back to step 3 and repeat until step size is very small or you reach the maximum number of steps. One last thing before we're done. In our example, we only had 3 data points, so the math didn't take very long. But when you have millions of data points, it can take a long time. So there is a thing called stochastic gradient descent that uses a randomly selected subset of the data at every step rather than the full data set. This reduces the time spent calculating the derivatives of the loss function. That's all. Stochastic gradient descent sounds fancy, but it's no big deal. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more, please subscribe. And if you want to support StatQuest, well, consider buying 1 or 2 of my original songs or buying.
Here, guys, hope this is enough to give you the idea about optimization. And also, as we said, all these videos links are already in OWL. So I will try to add, because I know that we have stochastic learners that sometimes they would love to read something in paper or in slides. So about the topics that we covered last lecture and this lecture, I will add some resources to help you and guide you about the topic we cover. But the videos are your main source of study for these topics, because it's rich with interactive example, with beautiful graphics. But also I will add some kind of slides that cover all topic and what we cover in the previous class and current class videos. Questions still here? Next class, I'll not start with classification algorithms. We will start next week with the classification algorithm. As I mentioned, the group project sheet will be ready by maximum tomorrow evening, and the guide, everything will be ready, how to pick your topic. Then you have to finalize your topic before next week class. Any questions? Any questions? If you don't have questions, you are free to leave. We'll leave earlier today. But if you have any question, anything regarding your group, you can wait and we can discuss after the other student leave. Thank you, guys. Thank you, everybody that's saying thank you. Thank you. You have a good day too, Perian. Thank you, everybody. Thank you. Thank you, guys. Thank you. I'll stop recording here, so if we discuss anything, it will not be recorded.